Hello everyone, welcome back. So today we will continue our stack data structure journey and we were on polish notations. If you remember the part 2 of this stack data structure series in which we did solving of infix expression using two stacks and then solving the postfix expression using a single stack. And then we also saw why postfix, which is also called reverse Polish notation, is mostly used in computer science world. So continuing this journey, what we are going to today solve is how to solve an prefix expression. So let's take an example. Before that, let's see what are the algorithm steps involved. You will be very happy and surprised to note that the steps are almost same as solving the postfix expression. This one. Steps are almost same. It is just one difference that I'm going to tell. And that first difference is we need to start from right side and move towards left. So in the solving of postfix expression, we started from here and we moved in this direction. Right? So we started from the left side and moved toward the right hand side. But when we solve a prefix expression, let's take any example. So it should be something, say 8, 3, like this. Say this is our example. Okay, so this is our left side and this is our right side. So we just need to start from here and move towards here. That's all. The other steps will remain same, which I can say I will copy from the above. Same. Right? And I can say that this is same algo as above. This is the only step that we added. Okay, and with this, let's start to solve this problem. So let's say this is our stack. We are starting from right hand side. First we got 4. Step number 1. Push into the stack. Next is 12. Push into the stack. What is next? Divide. It is an operator. Pop two operands. 12, 4. Apply the operator. So before that, we need to pop it out. So the result should be 3. So if we pop out from here, so what we can say is 3 here, and we can remove this because we have solved it. Now next is 2, push it, then 3, push, 8, push. Going very simple. Then we got a plus operator. So what we will do is we will pop two elements, 8 and 3. Okay, so and the result will be 11. So what we will do is we will remove these and put the result 11 back. Our next element is multiply. So again it is an operator. So what we will do is we will pop two elements. Answer will be 22. Remove these. 22 will be pushed back and this will be removed. Next again we are having an operator minus 22 3 because now we have to pop the operands and the result is 19, which we will push into the stack. Now we have traversed entire expression, nothing is left. So whatever is the final value in the stack, it is our answer. That's it. So simple. So from your exam point of view, if you know how to evaluate postfix, automatically you know how to evaluate prefix. Just remember, in postfix you have to start from the left and move towards the right, and in prefix evaluation you start from the right and move toward the left. That's all. Okay, with this let's move to another topic for today, and that will be how can you convert a infix expression to postfix expression. So till now we have seen how we are evaluating these, but we are constantly saying that postfix expressions are much faster than if a human is giving an input as say infix expression, then how it will be converted back to postfix. So that's what we are going to see next. Convert infix expression to postfix expression. That is what we are going to see next. And this is also very simple. If you remember how we evaluated the infix expression, just keep those steps in mind. If not, I would suggest please go back, see the second video of this series and then come back here. Okay, the steps are almost similar. Okay, so let's say we have an expression 5 plus 3. Let's include parentheses also to make it more interesting. Pretty good one, right? So we will try to convert this to postfix. So this is an infix expression, you can say. So before that, let's first write down the algorithm steps. So we will start from left and move towards the right. First point, if you get an operand, add it to output. Okay, add it to output. If you remember, when we were solving infix expression, we were putting in a separate stack. Here we will be using a single stack only, no need of two stacks, but we will just put that directly to our answer. Okay, if you get an operator, then if top of stack has higher precedence, then pop it and add to output. Else push operator to the stack. If you get opening parenthesis, push to stack, and if you get closing parenthesis, pop until opening parenthesis is found in the stack, which will always be there because we are assuming that the expression is a valid one. Okay, and if the expression is finished, then you can say that okay, whatever is there in the stack, keep popping it. So let's try to solve this using our example here. I will make sure that you keep on reading the algorithm steps here. Okay, now I think this should be good. Okay, so let's create our stack here. Let's say this is our stack. I think this should be fine. And this is our output. So we are starting from left. We got an opening parenthesis. So what we will do is see point number 3. Push into the stack. Again, we got an opening parenthesis. Push into the stack. Then what we got is 5. It is an operand, point number 1. Add it to the output. What we get next is plus. It is an operator. So there is no operator in the stack. It is a parenthesis. So push plus into the stack. Next is 3. It is an operand. Get it to the output. Next we get is a closing parenthesis. So we have to pop until we get a opening one. So we will remove plus, and when we remove plus, we will put that into our output. Okay, I will leave this is with red. That means we have popped it out from the stack, and then we basically pop out until we get a opening parenthesis. Next we get a multiply. So what we will do is we will push that into the stack. Again opening parenthesis. Then 8. So what we will do is we will get it to the output. Now minus. We will push into the stack. Next is 2. Make it to the output. Now again closing parenthesis. So what we will do is we will pop out our operand and add it to the output. A point of second. So we have to remove it from here, and we will remove till we get the opening parenthesis. Next we get is again a closing parenthesis. So we have to pop the operand and write it to the output. So I will remove this and the opening parenthesis. Then we get the operator. So we will push into the stack. Next is 4, operand, write it to the output. Expression is finished, pop whatever is left. So divide is left, we will pop that out and write it to the output. That is our answer. And we need to remove this divide from the stack, so that stack should remain empty when we got our answer. That's all. So next topic that we are going to cover in today's video will be on time complexity of various stack operations. Okay, so I will just write this here only. So time complexity of stack operations. So the first operation was push. And what should be the time complexity? It is of 1, which is called constant time. And why it is constant time? Because it doesn't matter whether your stack has 5 elements, 5 million elements, 5 billion elements, or it is empty. You will just push onto the stack and rest of the elements are not touched. Okay, so you just need a constant time to push something into the stack. Similarly, pop also, You just need a constant time to pop something from the stack, and peak or top, they also have constant time, because doesn't matter how many elements are there in the stack, you are just touching or popping or pushing the element at the top. Rest are not touched, they are not iterated. That is why stack is such a beautiful and widely used data structure. All the operations are constant time, no matter how many elements are present. Right? Fourth one is full or is empty. These will again be constant time, but with a caveat that these are implementation dependent. You can have a class variable which will store the size of the stack, the current size. If it is 0, you can say stack is empty. And if it is equal to the max capacity, you can say it is full. So it is implementation dependent, and most of the implementations do have this class as a member variable present, and by which you can tell that whether the stack is empty or full. Okay. Next one is solving infix, postfix, or prefix expressions. And time complexity for solving this is O of n, which is linear time. And why it is linear time? So here n denotes the length of the expression, right? So if n are the number of elements in the stack, so for each element we are going to perform some operation on the stack, and that each operation is going to take constant time. So it would be O of n. And similarly for converting the expressions which I have listed above among themselves, you will again be needing the linear time, where n is the length of the expression. But with the same logic as I explained for line number 5, because the stack operations are going to take constant time. Okay. Another thing is called space complexity. This means when you are performing an algorithm, how much extra space you are going to need. Okay. So for all stack based operations, your space complexity will always be of n, linear. N is the length of the expression, right? Because you at max, your stack can contain all the elements present in the expression. So that much space you at least need for your stack to solve the expression, right? So with this, we can say that we have covered in our topics time complexity, Polish notations also. In the next video, I am going to tell you about the implementation of stacks using arrays or linked list. Okay. Till then, I would request, if you think that I need to give more explanation, or you need some more explanation, or there's some topic that I am not able to cover, please let me know in the comments below, and I will make a video on that one. Thanks for watching. See you again. Bye bye.